So this lecture is all about sedimentary rocks. The last one was about igneous rocks, and then the next one will be about metamorphic rocks. So we're kind of almost halfway through talking about the rocks, the families of rocks. All right. So just a little joke to start out. So not sediment or not sedentary rock, just sedimentary. Okay, I can't even get my own joke out. All right, and here's a good example of some sedimentary rocks. So this is Bryce Canyon National Park out in Utah, and it's an excellent example. These formations are called hoodoos, and they're kind of a erosional feature when sedimentary rock erodes away. All right, so I've shown you this in the last lecture about the origins of rocks. So when we're talking about sedimentary rocks, they can form anywhere. They can form in mountains, they can form in beaches, they can form in deserts, they can form in lakes, they can form in the oceans, they can form all over. So sedimentary rocks basically can form in any of these different types of environments that you have over here on the left side. And this actually tells you what kind of sedimentary rocks, like sandstone or conglomerate or shale, and where they actually form. So let's talk about sedimentary rocks. These are kind of the easiest in terms of identification. If you were outside in the field and happen to be looking at some rocks, they tend to form in layers. So we don't have as many sedimentary rocks around here in Massachusetts, but if you went to the western US or really the central US in terms of like states like Kentucky, Tennessee, and a little bit west of there, they have sedimentary rocks. So they form in layers in many different types of environments. So this is sedimentary rocks that are going to eventually form, or this is mud that's eventually going to form into shale from a lake deposit. We have some loose pebbles here, which would probably eventually turn into something called conglomerate. We have a beach here. So if a beach turns into a sedimentary rock over time, then it would be a sandstone. So you start with sand, you end with sandstone. So they're going to form in layers in many environments. So for example, if you ever go to the Grand Canyon stores a very large portion of Earth's history. And each layer is basically one chapter book in Earth's history, which is pretty cool. But in the Grand Canyon, it's all sedimentary rock, at least in the upper part of the Grand Canyon. So there's like a sandstone layer, a shale layer, a limestone layer, another limestone layer, and we'll define what all those rocks mean in a second. So sedimentary rocks tend to have those layers, kind of distinct layers, almost like a layer cake. Just like there were categories for igneous rocks in terms of plutonic and volcanic, there are categories for sedimentary rocks. Clastic will have the most examples of, biochemical will have just one example, and then chemical will have a couple examples of. So these are kind of our three groups. We'll start with clastic, then we'll move on to chemical, and then we'll finish with biochemical last. So what is a clastic sedimentary rock? A clastic sedimentary rock is made of something called clasts. Clast is just the geologist term for like a loose pile of stuff, of material. So it could just be gravel, it could be pebbles, it could be sand, it could be silt, it could be clay. So if a rock has fragments in it that are made of gravel, sand, silt, or clay, it's probably going to be what we call a clastic sedimentary rock. And we'll go through some names here in a minute. If you take a clastic sedimentary rock and you zoom in on that under a microscope, this is taking a conglomerate and then you kind of cut it in half and then you could stick it under a microscope and look at it. What you would see inside of that rock is that it'll have like a cement that usually grows out of a water rock solution. So chemical solution basically leads to the formation of something that we call a cement. It'll have minerals that are in it. So it might have quartz, for example, and it will also have fragments of other pre-existing rocks in it. So you could have a chunk of granite in it. You could have a chunk of basalt in it. Just to use some of the names that we already talked about, it could have a chunk of rhyolite in it. So how do these form? They go through a process called diagenesis. Diagenesis is like a 5-step process of how you take loose stuff, like a pile of sand here, and you form a solid rock like a sandstone. So let's go through each of these steps in terms of looking at diagenesis and then how you can get a solid rock from a loose pile of stuff or a loose pile of material. So step 1 is weathering. Weathering is just the breaking down naturally of a rock due to either physical processes, so like ice forming a wedge and breaking apart a rock, or chemical processes like dissolution. So if you have acid that comes into contact with rock, it dissolves away that rock and weathers it away. So that's the first step. You start with a pre-existing rock in a given location. That pre-existing rock breaks down through weathering processes. Steps 2 and 3 are erosion and transport. So weathering breaks down a rock in place. Erosion is what actually moves that broken down stuff to a different location. And then transport, if it gets picked up by a river or ice or wind or something like that, then you can move it to another location. So that's steps 2 and 3. You get erosion and then you get transport. But just to show you the diagram here, weathering breaks down the rock in place. So these are the little chunks that have broken off of that rock. And then erosion and transport are what move those down the hill to a different location. So down here I have a question. What are some ways that sediment can be eroded and transported? Water, rivers, wind, gravity. Gravity can cause a landslide and move rocks that way. Gravity, rocks, rivers, ice, and wind are another way. Just to give you examples, so here's an example of a glacier. Glaciers move and erode and transport a lot of material. So the dark color in this ice here is all stuff and sediment that's being moved by ice. This is from wind erosion. So this geologic feature, basically there's sand grains here in the desert. When the wind picks up the sand grains, it'll just smack into the bottom of this formation and abrade it and erode it away over time. So that'd be wind erosion. And then this is a horseshoe bend in a river out in the western US, and that was created by water erosion. Let's add step 4. So just to remind you, steps 1, 2, and 3 are weathering, erosion, and transport. So by that point, you take a rock up in a mountainous area, you erode it, and you transport it. You might have moved it a pretty long distance at this point. So it's going to deposit, it's going to settle out and stop being transported, and it will deposit somewhere on Earth's surface. So an example of deposition, if whatever is carrying that rock stops moving or slows down, then that rock or that sediment is going to settle down to the bottom like a leaf falling off a tree that settles once the wind slows down or stops blowing. This is a delta here. So basically a river is meeting the ocean. And then the reason you see all this cloudy, muddy material is because you have a fast flowing river that meets slow moving ocean, and all of that material just starts to settle and drop out. So that would be sediment deposition. So we're almost done with diagenesis. The final step is what we call lithification. Remember, lithosphere is solid rock. Lithos means rock. So lithification is the act of taking a deposit of sand, for example, and then turning that loose pile into a solid, compressed, solid rock. So how this happens is that the way sedimentary rocks will form is that if you have some kind of erosion that brings material to a location, then it will form layer by layer by layer. As that sediment or whatever material is settling out, it'll form layers and layers and layers. And the more layers that you add, the more you compact and compress those particles of sand together. They get closer and closer and closer. And then over time, they'll glue together with the cement due to chemical reactions that we won't talk about, and you'll get a solid rock. So lithification is the act of taking loose material, you deposit, it compacts, then it compresses, it will form a cement, and you'll get a solid rock from what used to be a loose pile of rock somewhere, or a loose pile of sediment somewhere. So let's talk about some names. So we're still in clastic rocks here that form through the process of diagenesis that we just talked about. So the names of rocks depend on what we call the clast size. So if it's made of boulders, we call it something. If it's made of pebbles, we call it something else. If it's made of sand, we call it something specific. If it's made of sand, we call it something else. If it's made of clay, we call it something else. So there's a relationship that occurs though. So if you have a large grain size, like a boulder or a cobble or a pebble, those tend to be located very close to the original source of that rock. And the reason is because if you take a rock and you transport it, it gets abraded as it kind of spins and bounces along, and it will get smaller and smaller and smaller. So the smaller something is, the farther it has been transported away from its source. So large grain size means it's close to its source. Small grain size means that it's farther from its original location. We can also identify clastic rocks according to their angularity. So if something is angular, basically it's pretty close to its source because it hasn't been tumbled and kind of smoothed out by the process of erosion and movement and transport. So if it's angular, it's very close to its source. And then if it's rounded, it has been moved a very long distance, has been abraded and kind of rounded and smoothed over time. All right, we can also classify rocks. So we got grain size, we have roundedness. We can also classify it by what we call the sorting. So the sorting tells you what percent of the clasts or the grains are the same size. So there's a scale here. Basically, it can be ranked from very poorly sorted, which just means you got a lot of the large stuff, you got a lot of medium-sized stuff, and you got a lot of small stuff mixed in there together. So it's just a mess, basically, in terms of what stuff is in it. If you go to moderately sorted, you kind of have some smaller stuff and then some slightly bigger stuff, but it's not as drastic of a change from the very poorly sorted one. Well sorted means that every single grain is about the same size. So think of like a beach, a nice sandy beach. That's very well sorted because all of those little sand grains are about the same exact size. So based on that, you have your quiz questions that you can start to answer. So you have a picture here. This is showing you a picture of a deposit. What you need to do is that you need to examine the angularity and the sorting of this deposit and pay attention to the scale on the image. So this is telling you that this is about a foot across. And then given the distribution of grain sizes in the image, do you think this deposit is located close to its source or is it far away from it, kind of based on what I was just talking about? You have a second deposit that you're going to examine. So again, for scale, this is showing you that this would just be about 2 inches across. So I want you to examine the angularity and the sorting of this second deposit. And then given the distribution of the grain sizes in the image, do you think this deposit is located close to its source or is it really far away from its source? So let's get into some names. So if we're talking about the names of sedimentary rocks here, we're going to start with the largest kind of grains to begin with, and then we'll work our way down to the smaller ones. So let's say you start with gravel. You have a river that has pebbles kind of on the side of it. Those pebbles get buried, and you have pebble or gravel, and that goes through that process of lithification or diagenesis, so forming a solid rock from a loose pile of material. We call it conglomerate. So conglomerate is basically a sedimentary rock made of pebbles that have been kind of glued together over time. Let's say you start with sand. So if you start with sand, you can get sand at the beach, you can get sand in the desert. If that sand gets buried and over enough time it turns into a solid rock, you get sandstone. So you start with sand and with sandstone. So sandstone, if you had an actual sample of it, it's really gritty. So if you kind of rub your hands against the edge of a sandstone, it's really gritty and kind of rough, just because it's made of sand grains, all compacted and compressed together. Let's say you start with silt. So silt is more like kind of flour or the size of like table salt, if you want to think of that. If you take silt, you turn that into a solid rock, then you get silt stone. And then lastly here, if you take mud or clay and you turn that into a solid rock, you form either mudstone is a term for it. You can have claystone is another term for it, or shale would be another example name. So you start with mud, end up with shale. All right. So here's another bad joke. So why was the sedimentary rock extra cheap? Because it was on shale. All right, so at this point, you should be able to answer questions 6 and 7 on the quiz. Feel free to pause, come back when you're done. All right, so we're a third of the way through. We got chemical and biochemical left to finish up here. These will go faster than the first part did. So chemical sedimentary rocks, if you've ever been in a cave, you've been surrounded by chemical sedimentary rocks. So they're very common in cave deposits and then deserts as well, as I'll go through in a second. All right, so chemical sedimentary rocks are classified by their chemical composition. So they're going to form through chemical reactions, and then usually they will form out of some kind of solution. So in case you don't recall what a solution is, it's just a mixture of water plus something else in it, usually dissolved. And then you can take a solution and you can either evaporate away the water through a just general evaporation process, which we'll look at, or you can do what's called supersaturation, and you can cause something called precipitation, where you get a solid mineral that will come out of that solution of water that you have. So let's talk about an example of a chemical sedimentary rock. An example is salt. So minerals can crystallize from solution. So let's say you have a mixture of salt plus water. The salt is dissolved in the water, but let's say that water evaporates away. So you got kind of a lake environment. You have salt that's dissolved in the water, and then the water evaporates away. Water only evaporates as pure water, so it leaves the salt behind, and then you can get these deposits of crystals of salt that form on like a desert floor, as an example. So a good example of this is like if you've been outside sweating on a hot sunny day and you get these crystals of salt on your face. Same process. You had a solution of salt plus water in the pores of your skin. The water evaporated away. You have the salt crystals left on your face. Same thing happens in a desert environment to form salt. So you might have seen videos like this before. So this is from an elementary school, but basically you can take, I will leave this. All right, and I'll speed this up. So you can take a solution. You could do this at home. Just make a solution of salt water, mix it up, put it on your counter, let it evaporate over a couple days. And what you'll see is that you'll get this crystallization of salt forming as the water evaporates away. Salt recrystallizes in your little petri dish or cup if you're going to do an experiment like that. Okay, so we call these evaporites. That's the sciencey term for it. So if you're doing your sedimentary rocks homework, there is a question on there that asks you about something that evaporates from water. It's called an evaporite. Examples of this are halite, which is table salt, sodium chloride here, and then gypsum, which is what drywall or wallboard is made from. So evaporites are basically minerals that form when water evaporates away and leaves behind the remaining material. Another example of a chemical sedimentary rock is limestone. So limestone can be chemical or biochemical, which I'll talk about in a second. If it's biochemical, it's something that formed in like a coral reef deposit that's made of shells, but it can also be what we call chemical. So caves are usually made of limestone, and stalactites and stalagmites, those kind of cave features that you might have learned about before, they're made from limestone. Where this comes from is that you take a solution, so you got a mixture of water and stuff dissolved in it, and if it gets so concentrated to the point that we call it super saturated or oversaturated, you can actually get crystals that will form out of that water. That's called precipitation. So when that happens enough, if you have a water solution like this here, that water solution, if it becomes oversaturated or super saturated, then it creates limestone. And that's where cave deposits come from. As an example, let's say that you could do this with like sugar, a solution of sugar and water. If you add enough sugar to it, you can cause it to form crystals out of that solution. So it's kind of like this mechanism here where you have dripping of a super saturated or oversaturated solution, and then you can form this kind of little stalactite or stalagmite with a dropper in the top. Same thing with a cave. If water is dripping through rock, it can become oversaturated or supersaturated, and that dripping of that water forms stalagmites and stalactites. All right, this isn't the most clear animation here, but it's kind of showing you how a cave deposit can form. So you get cracks in rock, and then as water moves through those cracks in rock, it dissolves the rock around it away. But if you have enough of a saturation of that solution, then you can carve more parts of a cave and you can form those deposits like the stalactites and the stalagmites over time. All right, so almost done. Our last one here is biochemical. So a biochemical sedimentary rock forms from something that used to be alive. So that's why it's called biochemical. It used to be alive. The biochemical sedimentary rock, the example that we'll talk about here is coal. So coal is commonly used for fossil fuels. It's not as used as much now as it used to be, but for energy production, the U.S. still burns a fairly large amount of coal to create energy for power plants. So what coal used to be is swamps. So roughly 300 million years ago, the conditions were right to form coal. So you had all this vegetation in these swamps, and that vegetation died back, got buried. So you have this plant matter here that got buried under some mud, then some water. With enough time and enough pressure and enough compaction of that swamp material, it transforms into coal over time, and then you can mine out that coal and burn it for energy. So biochemical, because it used to be alive, it used to be plants, now it's a solid rock, so we call it biochemical. The last point that I want to make is that many fossil fuels that we have, I just talked about coal, but oil and natural gas are typically found in sedimentary environments. specifically sandstone. Sandstone is pretty porous, so if you find oil and natural gas, it tends to be trapped in sandstone or limestone in some cases as well. So the graphics that you have on here are just showing you different locations in terms of like geology where you can find oil in different locations. All right, so at this point, you should be able to finish the remainder of the sedimentary rocks quiz.